today we are doing the simulation of Turing machine by recursive functions. So let's just quickly recap where we are. So where we are is, so let me show you the theorem maybe first. So this is the theorem that if M is a one-tape Turing machine and it computes some function, the idea is that we want to show that this function can be is mu-recursive basically. So what we proved before was that if you had so we had mu-recursive functions. So these were functions like projection and successor and constants and recursion and so on. So we created class of mu-recursive functions, and then we proved that they are computed by Turing machines. So now I want to go back, right? And I want to say that if I have a Turing machine that computes a function, that function is mu-recursive. And I already proved that any Turing machine is basically a one-tape Turing machine, can be simulated by a one-tape Turing machine. So without loss of generality, I can assume that I start out with a one-tape Turing machine. So this is what this lemma says here, that I start out with machine M. This is a one-tape Turing machine, and it computes some function. What this means is basically that so I start with some tape that goes infinite on both sides, and I have some number written here. Actually, so it takes k many inputs, so maybe I have some, I don't know, whatever. So you have some many inputs written out here, separated by a hashtag, so k many inputs. And you start your machine, and it gives you one output. So it gives you some output, I don't know. So it gives you some output like this. And then I say that this function can be computed this way, meaning that exactly what this machine does is exactly what this function. So this is exactly what this, so this one-tape Turing machine that I wrote down here exactly computes this function. So it may be any function you know, and I want to prove that if there exists a Turing machine that computes a function, that function is mu-recursive. And basically what this says is that if you can write an algorithm, by algorithm meaning a Turing machine, that computes a function, it's same as saying that that function can be constructed from constants, projections, and so on and so forth, mu-recursively, basically. So this will conclude the proof that everything that is computed, so mu-recursive functions and Turing machines are basically the same. So things that Turing machines compute are the same as what mu-recursive functions do. And so let's do this, and it entails. So what we do really, so this is probably something you have not seen before. So this entails actually coding everything into natural numbers. And this kind of shows you how natural numbers are enough to encompass everything that is computable. So what I will try to do is, so I know that there is a Turing machine that takes an input and gives me an output. So this is my function, right? Takes an input, produces an output. So now, in the middle, this Turing machine does funny things. Basically, it works on configurations. So it changes one configuration to another, blah, 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 and it gives me the output. So what I want to do is to change every step of this Turing machine into a mu-recursive function from natural numbers into natural numbers. And then I will just compose this mu-recursive functions that I will define that will exactly simulate what the Turing machine does. Maybe it's confusing, but let's start. So let's see what I'm trying to do. You will see what I'm trying to do. So I have this Turing machine, right? So it takes a k many inputs and produces an output, and I want to show that this function is just like a composition, basically, of mu-recursive functions. So every step of the Turing machine is just computing some mu-recursive function. This is what I want to show. So what is my Turing machine, right? A Turing machine is 5 things. So it's a set of states, an alphabet, a transition function, most importantly, a program, a start state, and set of end states. So first, this is my, so I want to translate this all into numbers now. This is a weird thing that you might not have seen. This probably goes back to Gödel, this idea. So what we do is, so first what I say that let's first assume that states and alphabet are disjoint, meaning states have different letters than the alphabet. This you can always do, you just rename states. So if you had the same letter used for alphabet and for a state, you just rename the state and it's the same machine. So I just assume that states and alphabets are different, and then I look at the set of states and alphabet. So I take all states and alphabet together and I name them A1, A2, A3, A4, A5, A6, however many, there's a finite amount of elements in the alphabet. Alphabet is a finite set. Z is also a finite set. So if I take their union and if they're disjoint, which I achieved by renaming states, let's say, then this thing will be a finite set. So if I have, let's say, 3 states and let's say, I don't know, 6 alphabet symbols, then I will have A1, A2, A3. I will just rename states A1, A2, A3, and the alphabet symbols, I just rename them A4, A5, A6, whatever. So this is just give them, basically what I'm doing, I'm giving them numbers. So from 1 to P. So P is the number, whatever this number is. And now, the configuration of Turing machine looks like this, if you remember. So you have a string, so it looks like this. So this is a configuration of a Turing machine. So you have something like this. So, and you have, I don't know which letters were we using. So let's call this guy A here. And then you have a state, like your Turing machine is in state Z. And this whole thing we called U maybe, and this whole thing we called V, right? And we would write this configuration as U, Z, A, V. So this is actually a string. This is a string, this is a string, this is single symbol. Because this is like V1, V2, maybe this is, I don't know, U1, U2, U3. This is horrible, I'm going this way and this way, but that's okay. So you have a string here, you have a string here, and a symbol here, and a state, like this. And you code this way. This was my configuration, and I knew how to go to the next configuration according to delta. So you look at what is delta ZA, and then you act accordingly, right? So this is my configuration, right? So what is the configuration? Configuration is the string in these symbols. This is the key observation. So if my states are now A1, A2, A3, and if my alphabet symbols are also A1, A2, A3, every configuration, let's say U, Z, A, V, is basically a string. So this is a string in, if I take A union Z plus. This plus means that this is a not empty string because configuration cannot be empty basically. So it's just a string in symbols of alphabet. So A, V, U are alphabet symbols, and Z is just a state. So a single state can also occur. So this is a string in symbol states and alphabet. Now each one of them are mapped to A1 to AP, right? I renamed each string symbol from A1 to AP. So now what I'm doing is I'm changing it into numbers. So I'm changing strings into numbers. So let's look at an example so we're not confused. Let's say our alphabet is just what? Alphabet is B and a hashtag and blank. So this is, let's say this is my alphabet, right? Then my configuration can be something like this, right? Z17, I don't know, 1101. Maybe blank here. So this can be my configuration at some moment. That means I'm in state Z17, I'm reading 1, and this is on the right, this is on the left. And I want to change this into a natural number. I want to code each configuration as a natural number. And how do I do this? How I do this is that now, first, I know that each letter corresponds to one of the AIs because I numbered each state and each letter by A1 to AP. So this might be A7, this might be A4, and so on. And what I do is I define this function psi that to each I assigns I. Let's look at an example. So let's look at a very hypothetical example. Let's say my alphabet is 0, 1, blank, and hashtag. And let's say how many states I have. Let's say I have 5 states. Just for simplicity, you will see why. 3, Z4, and Z5. Right? So I just renumber this, guys. What I say is I just call this guy A1, A2, A3, A4, A5, A6, this is here, by the way, A6, A7, A8, and A9, okay? So I have 5 states, 4 alphabet symbols, so I have in total 9 symbols. So what psi does, psi of 0 will be 1, because it's basically what it's doing is it's psi of A1 and it's 1. Psi of Z3 will be 7. You get the point, right? Because Z3 is A7 in my renumbering. I could have done it many different ways, but I just did it in one way. So now each letter so each state and each letter of the alphabet has a natural number assigned to it. Right? Great, so this is what this thing does. And now what I do is I want to extend it to strings. How do I extend it to strings? Let's say B is my string here. So let's say B is a string that is of length L. What I do is I interpret it as a number in base P plus 1. So I look at the string like this, and I write it in base P plus 1. So in our example, what this thing does, what is P in our example? P in our example is 9. This is why I took 9, just because it's much easier, because we were used to decimal base. Then P plus 1 is 10. So I'm going to interpret strings as just base 10 numbers, the ones that we're used to. So for example, if I have a string like this, 0, 1, 1, blank, Z, I don't know, 4, 1, hashtag, what number does this correspond to? I just interpret this as a decimal number. What does 0 correspond to? 0 corresponds to 1. 1 corresponds to 2, so it will be 2, 2. Blank corresponds to 3, like this. Z4 corresponds to 8. 1 corresponds to 2. And hashtag corresponds to 4. And this is like natural number 1,200,020 or 12,200,038, 238,000, whatever this number is. This is a natural number. But what I did is, since these guys have now their numbers, but this was 2, 2, this blank was 3, and so on, I interpret them as base P plus 1 numbers. But there's a caveat here. I chose the P to be 9 and P plus 1 is 10 because it's so easy. Then you just replace numbers here. But P can be bigger than 10. Let's say P is 16 or 15. Then P plus 1 is 16. Then you have to write things in base 16. And that means that one symbol in an alphabet, for example, can be mapped to 2 symbols in natural numbers. See what's happening? Because if it's 11th number, let's say, and you're in base 16, you will have 11 as a single symbol in your natural numbers. This can also happen. So do not let this mislead you that it's this easy sometimes. Because let's say I'm working in, if it's P is 16, as I said, it might happen that your blank is 14, and then when you're mapping, there's something here, then you will have 14 here, but this will only represent one symbol. Here, each one of them represents one symbol, and it's easy. So you can translate back, but it might not be the case, because you will not be able to tell easily whether this represents two symbols, 1 and 4, or is it 14. But somehow I want to see that, and that's why when I look at the representation in the base, this is the base representation, right? This is exactly what it means. For example, when you have, let's say this is a huge number, but let's say I mapped something to 901. What is 901? I want to see it as 9 times 10 squared plus, well, 0. Okay, so let's get rid of 0 so it's easy. So it's 9 times 10 squared plus 3 times 10 plus 1 times 10 to the 0. It's like this, right? In decimal expansion, but you can do it in generally. This is exactly p plus 1, however many symbols you had in your alphabet plus the states. And this is what is written here, that psi bi is just the code of that symbol times p plus 1, in our case is 10, the powers of p plus 1. However, whatever p is. Let me pause this so you can ask questions. I have not said, so let's continue recording. So there are no leading zeros. What I mean by this, that if we go to pen, so there's no things like this happening, because there's nothing that is mapped to 0. So this might be this. So if you look at, this is not even a natural number like this. You might think of it as 991, and then you might think of this guy also as 991, and then you will have two different strings corresponding to the same thing, but this is not happening. None of them are mapped to 0. They start from 1, so every single symbol is mapped to a natural number. Thus, this thing is injective, meaning that every single string is mapped to a unique natural number. That is the idea. So what we did is we coded strings into natural numbers. So instead of looking at strings, I look at natural numbers. This is actually a very deep idea if you think about it. So that means you can map strings. This goes back to saying that, remember we said that finite strings, A star, was countable. That means there was bijection, one-to-one correspondence between natural numbers and strings. But now we're actually constructing this computably. So for every string being a string in, so string being string in this one, we got mapped to a natural number and it's unique. And why I say it's a deep idea, because then whatever this says, that everything, if you investigate natural numbers enough, it captures everything, because every single possibility of all possible strings can be mapped to natural numbers. But okay, so let's forget it for a moment. This is what we're working with. So we're writing things like this. Now what I want to do is I want to look at the code. So I'm looking at the natural number and I want to guess some properties of the string. So first of all, I want to guess the length of the string. So what I'm asking you this. Let's say I know that the code is this. What was the length of the string?
7.
Yes, in this case this was 7. But the question is, how did you know that this was 7? Because if my p, let's say p was bigger than 10, it might be that there's, let's say again 16. Let's say my p is 16 again. So you somehow have a connection with 16, so let's make it 17. So let's say p is 17. Then it might be that this guy here is a single symbol. How would you know then the length of the string? აი როგორ exactly I'll show you. So all of you are in a correct direction. So this is what this thing is saying. So it's an operation, and I want to guess the length of the b somehow mu-recursively. This is what I mean. So I know that psi b is x means that b is some string of length L, and the code of b is x. X is my natural number, which is the code of b. And I want from x, I want to guess L, because f is the length of b. How would I guess this? What is L of x is the length of whatever x codes. And this says this is the smallest j. First of all, j is less than x, because if your code is x, your length cannot be longer than the code, because your code codes 1,200,000 whatever. Your length of the string cannot be longer than whatever the number this thing codes. So this is bounded, so it cannot go past this. So it's j, such that j is less than x, and p plus 1 to the power j is bigger than x. Can you guess why? Or can you justify why? Let me pause this and then we can. So let's to continue recording. So let's look at the example. By the way, I'm showing you the example with 10, but this is a deceiving example. Claiming that this thing deceives you, meaning that you're very much used to tens. So let's say p plus 1 is 10, and let's say I have the strings 2, 9, 6, 3, 1, 4. And so how would I guess what is the length of the string that actually gives this? It has to be 6, because in base 10, every code has length 1, as we saw. So it has to be, how do I guess 6? What is 6? 6 is the first power, such that 10 to the power 6 is bigger than this, and 10 to the power 5 is smaller than this. This is all this thing is saying here. That it's the smallest power such that 10 to the power j is bigger than x, and 10 to the power j minus 1 is smaller. So this is size 6 because it sits between 10 to the power 6 and 10 to the power 5. And you can do same thing for general p. So you can guess so if I give you a code, even though some of the numbers there might represent just one symbol, even then they're long, you can still do the same thing. And then you know p, right? So you can calculate p to the power j. You calculate p to the power 0, check, is it bigger than x? P to the power 1, is it bigger than x? And you do it up to x. So it's a for loop. For j goes from 0 to x, you check this. And the bounded for loop we saw, it was called the bounded mu operator. This is mu-recursive function. So this is a function that takes in x, a natural number, and returns you the length, and it's a bounded for loop, so it's a bounded mu operator. So you can really write a program to do this, so this is computable. So from the code, I can computably tell you the length of what was coded. This is number one. Okay, then what? Then next. Now I'm telling you, I want to give you the code of the prefix. So what I mean by this is, so here let's go back to, let's say, okay, I told you, okay, this is the code of x. This 1, 2, 2, 3, 8, 2, 4. And what is the code of this string here? What is the code? So what I'm asking now, let's erase this so we can see. So what I'm asking now, what is the code of 0, 1, 1b? Can you tell me from this? Yeah, it's the first 4 symbols, right? 1, 2, 2, 3. How did you know this?
Because each symbol represents each natural number, so it is very easy. So
But now this, look, so but But this here, this one here represents 1 10 to the power, whatever this is, 6, right? This one here represents that. 1 10 to the power 6, I got it. 10 to the power 7 maybe. How many zeros? Yeah, 6. 6. But this one here represents 1 10 to the power 3, right? That's why we're in base 10 and it's easy to guess, but I want to see how are you guessing this? This will work for all.
I subtract how many symbols I have on this side.
Exactly. This is what you do. So here is the enlargement. Prefix xi. What I want to do, I want to recover the code up to I, the first I symbols from 1 to I, is I divide x by p plus 1 l, the length minus I, and I round down. It might seem obscure, but like for example here again. So let's go back. How would I do this? What I would do, so I have this number, right? So I have this number 1 2 2 3 8 2 4. What I want to do is I want first 4 symbols, right? So the length of this guy L of x is 6. And I want first 4 symbols, right? So length is 7, right? 1 2 3 4 5. Yeah, length is 7 and I want first 4 symbols. What I want to do is I want to divide this by here. So I want to bring my comma here. So I divide this guy 1 2 2 3 8 2 4 to the 10 to the power what? 7 minus 4. However many I want in the beginning. This will give me 1 2 2 3.824, and then I round it down and I get 1 2 2 3. And that works in general. Exactly what is written here is that I take my code x, I divide it by p plus 1, the length minus I, 7 minus 4, so in our case 7 minus 4, and then I round it down. And I exactly recover the first part. And we saw earlier, I forgot to remind you, that division is primitive recursive, rounding down, powers are primitive recursive, rounding down is primitive recursive. So this thing, finding the code of the prefix of your thing. So you have a natural number and you want to some code and you want to find the prefix. Finding the prefix, it's the code of the beginning of your string, is an operation which is mu-recursive, meaning you can write a program to do this. Okay, and here is the same example. You translate comma and round down. Now, what about the suffix? The suffix is the tail part of your. So now I have the same thing, but now I have the same thing as here. But now let's say I'm asking, I want the code of this guy here, these 3 guys here. What is the code of these 3 guys? It is what? 824, right? 824 is the code of these 3 guys. How would I get 824 from this one? Yeah, exactly. So it's the remainder of what? Huh? Exactly. So this is exactly what it's. Rem means remainders. So you divide x by, in our case this is 10 to the power 7 minus however many things you want to translate, minus I plus 1. So you divide, in our case, this would be, so let's say here you want to pull out, changing to pen. So let's say you want to pull out this here, then what you do is you divide the whole thing by 10 to the 5, and then you look at the remainder. And this is exactly, again, we know that finding a remainder is a primitive recursive thing, and this thing is also primitive recursive. So let me just recap what we did. So what we did is every string now corresponds to a natural number. So this I called coding. So every string is now coded into a natural number. So now I'm looking at the natural number. First thing, I can tell how long the string was that was mapping to this natural number. This was 1. I can tell any first part of my string and any last, so any prefix and every suffix of my string, what is the code for that particular part of the string. And I can do it mu-recursively, meaning the computations that I have to do to figure out these codes of the beginning and the end and the length are all mu-recursive computations. Okay, so what? So now I have a code and I can figure out many things. What about the head? The head of the string is basically, I'm asking you, what is the code of this guy? It's the same exact thing. It's prefix of x but 1. Because I can do it for any I can do it for 1 as well. So in this case, it's 1. So this is what it says. The head of my x is the code of the first symbol, and the code of the first symbol is the same as prefix of the whole thing up to 1. Now, how would I select? What is select? What I want to do now is, so this is my question now. So let's say I know this again is my code. And what I want to do is okay, I know I'm looking at this code here, I know this, and what I'm asking is, what is the code of blank? How would you tell me? So you can tell me the code of any prefix and any suffix. Can you tell me then for each symbol, can you tell me what is the code of the symbol, only looking at this one here? Exactly, so you will find the suffix of this guy and then the head. This is exactly what it says here, is the select xi, also I denoted by xi, is the code of symbol bi, and it's you first find the suffix and then find the head. And head is basically what? Head is prefix of x1. So you first find the suffix and then the prefix. So now I extend it even further. Looking at the code, meaning a natural number, I can tell you how long your string was. I can tell you the code of each symbol in your string, and I can tell you not only code of each symbol, but rather each prefix and suffix, I can tell you the code. Okay, so what? Now, the question is, let's say I have two codes. Let's go back here. Let's make it shorter. So let's say one code is 132, let's say P is 10 again, just for your convenience, for 7, and the other code is 2456. So this is some string U, I don't know what string U is, and this is some string V. Can you tell me what is the code of UV? If I put those strings together.
We sum up their lengths and we map one.
So this should be, let me help you. So this should be something like this in base 10. But what is this? Can we generalize what is this as the powers of 10? Exactly. So this is exactly what is happening here. So what is the code of, so you take x, which is the first string, you multiply p plus 1 in our case in the power of the length of the y, and you add y. because this basically adds zeros in the end, and then y just comes in. So now this is again primitive recursive. Well, it's primitive recursive also, but this is mu-recursive in general. So meaning, if I have two codes, I can give you a code of the concatenation of the strings mu-recursively, basically. The computation I will do is a mu-recursive computation, and I can construct this. And of course, I can concatenate 2, I can concatenate 3, 4, 5, 6. So I can do it recursively. How do I concatenate 3 strings? First, I concatenate codes of u and v, and then w. How do I concatenate 5 things? First, I concatenate these 3 things, and then 2 things, and so on. So I can do it as many times as I like. So now I have all these operations I can do just looking at the code, right? So if I have 2 codes, I can tell, oh, okay, if this is the code of x and this is the code of y, this is the code of xy. But there's subtleties here when by the way, in base 10 it's invisible because every single thing is just a single thing here, and it works very nicely. But if the base is bigger, then it might be that 2 symbols represent one thing, and I will encourage you to think about it. Okay. Now, what I want to do is I want to look at the natural number code, and I want to tell you whether there is a state in the string or not, for example. What I mean here, number 8, right? 8, 1, 2, 3, 4, 1, 2. Yeah, this guy here represented this guy here we can call select, whatever. This represents Z4, right? So I want to kind of be able to guess which ones are the states and where they sit. Basically, what I want to do is I want to be able to, before I would look at the configuration and see exactly what the Turing machine is doing, what I'm planning now is to look at the number and somehow see exactly what Turing machine is doing. So I'm translating Turing machines into natural numbers. And this basically, again, this is why it's philosophically important. Somehow manipulations of natural numbers encode everything computable. This is what it would mean by Church's thesis. But how do I do this? First of all, well, codes of states is a finite thing, right? Remember? So what is in our case, what is phi of z? That means these are all possible codes of state. This is 5, 6, 7, 8, and 9 in our case. These are all codes of states. This is finite. This will be always finite because why is Z1 here? It's just Z. So this is always finite. So now if you remember when we had primitive recursive predicates and stuff, you can always check whether y is in psi of z for any number. Primitive recursively, actually, well, in general, mu-recursively, but primitive recursively also, because how do you check this? This thing is finite, you check is y 5, is y 6, is y 7, is y 8, is y 9, and it's computable. Since this is finite, whether this has answer yes or no, so the function that gives you 1 when this is here and 0 when this is not here is computable because you just check finite things. So what this says here, that this predicate, whether any number is here, is computable. In our case, in our example here, I can just run and check, is this guy there, is this guy there, is this guy there? I will get all no's here, and here I will get yes. So I will just check finite things at every single step, and here I will guess that this is the state. Nebismieri ritsui. This is all this thing is saying, and here basically. So now, if I can do this, I can also give you a position. So what I mean here is, I'm looking at this code. So I'm looking at this code again. So I'm looking at this guy here. And let's say I started checking and I know that this guy is Yes, so this guy represents Z4. Well, I don't know, but this I know that it represents a state. And now I want to give you a position of the state. That means an index on which number the state is. So I want to give you the I. So basically I want to tell you I such that the I symbol in my string is a state. In my case, I is what? So in my case, I is 5. This says that the fifth symbol in my string is the state. How would I guess this from here? In decimals, it's just 1, 2, 3, 4, 5. It's the fifth guy here. But it might be that this 12 represents one symbol, and it's not that easy anymore. But how would I guess? Just, okay, I know that 8 represents a state, but how do I know now that which string symbol is this first state? So basically what you do is, it's smallest j, again, such that j is less than x, and now I can select each one. So I first set j equals 1, so x1, this guy here, this is basically select from xi. So this just select xy. So this just gives me the code of the I symbol. So first I check the code of the first symbol, code of the second symbol. So it's again the bounded minimization. It's the smallest step such that that step, when I'm on that step and I'm checking the symbol, it's in the state. So this is again the bounded minimization. Let me pause this again. So what is this? So this is a good question actually. So what is this select doing? Select 1, 2, 2, 3, 8, 2, 4, 1 gives you the code of the first symbol. This will return 12 if the code of the first symbol was 12. It cannot happen in base 10, but if my P was 16 or something like this, then this can happen. And what select does, it returns the code of the first symbol, not just the first number. This is how we defined it. This is the idea. And this will return you this, and then it will check whether this is in codes of states. And this way, here, this way, the bounded minimization again will find you the state. Once the state is found, it's very easy to find all the, so now look what's happening. So let me, we're out of time. So let's continue after the break. Okay, let's collect our thoughts. So what are we doing, basically? So right here, let's go to our drawing board and just recap. So we have strings, basically. So let's say U1, U2, U3, then I have a state, Z4, and then I know A, V1, V2. So this is some kind of string. So this is supposed to encode the configuration. Well, it does encode the configuration of some Turing machine. And what I did with my psi here, I changed it into a number. So this might be 2, 1, 3, 4, 1, 2, 3, I don't know. So I changed it into some number, which is, let's say for our convenience, P is 10. That means the number of alphabet symbols and states is 9, right? So well, P plus 1 is 10. So the number, this is P and this is 9. So what I did basically, so I go from strings to natural numbers, and I gave you a bunch of different ways by just looking at the string and doing the μ-recursive computation. How can you guess, okay, this 2 is a symbol that stands for U1, you can tell me, or you can tell me, okay, this guy here stands for the state, and you can tell me, okay, state is number 4 on this string. So symbol number 4 on the string is a state. So you can tell me these things by just looking at the code. Okay? So now what I want to do is basically, oh, by the way, if you know that this guy is I is equal to 4, meaning that the state, let's call it, let's make it a different state so it's not confusing. Let's say it's 8. So you know that the state in the string is in position 4. You also know the position of the letter and also know this position here, right? This is basically I plus 1 and this is I minus 1. So you mu-recursively know exactly where the state symbol is, and you of course know which symbol state is looking at, for example. If you know this place, you know the next place and the previous place, right? So just by looking at the code, you can tell all this information. Okay, this is this configuration basically. So I know every single symbol. I know where the state sits. I know what is the symbol that my Turing machine is looking at, so on and so forth. But now, most importantly, what I want to do. So I have this string here, right? So I have this number here. I want to change it into a different number, so that it directly corresponds to the next configuration. So this one, as a Turing machine, has a next configuration, right? Maybe written this way. So next configuration might be something like U1, U2, U3, let's say Z14, B, V1, V2. So this will happen in case your head did not move, meaning if you had the transition like this, right? So you had delta Z8, what A was equal to, let's say, you changed it into B, went, well, first we write the state. So you go to state Z14, you change your A to B, and you go neutral. If this was the case, this will be your next configuration. You all agree, right? But this also has a number now associated to it. So this might be some, I don't know, 3, 3, 2, 4, 5, whatever. This also has a code. And I want to create a function that assigns to this code exactly this guy here. So in that case, what I will be able to do is I will be able to translate everything into natural numbers. And if this function here is mu-recursive, this assignment of numbers to numbers, which corresponds to assigning a number to a next configuration, then that would mean that I can simulate what my Turing machine is doing by basically playing around with numbers, assigning numbers to numbers, and doing it mu-recursively. This is what I'm trying to do. By the way, this is exactly what I said. So if you know where the state sits, you know what is the next. So this is Zx. So Z tilde X is where the state sits. So 1 to the left is AX. Exactly the state is where the state sits. BX is 1 to the right. And the U is the prefix and V is the suffix. So you can, if you know where the state is, you know where the first symbol is and the second symbol and everything. So we already said this. But here is the most important part. The one that I was describing you now is, so these 3 lines which contain the world of computation. So I want to define a function that takes in a natural number and spits out a natural number so that it exactly follows what is supposed to be the next configuration code, as I described. So what does this function do? This function takes a code of AZB. So AZB is a configuration when I'm in state Z, I'm looking at B and A is to my left. So A is just one symbol, which is to my left. So it's this configuration. It's very inconvenient that I cannot draw. So it's the configuration like this. So I have symbol, so I have, let's say like this. So A is here, B is here, and Z is here. It's this configuration. Whatever is here, I don't care. Right? So it's like this. So now this configuration AZB has a code. What this function is supposed to do is supposed to take this code and give me the code of AZ prime C if when I'm in state Z, oh, there's confusion between A and B. A is supposed to be here and B is supposed to be here. Let's change it, otherwise it's confusing. So this is more like this. A is here, B is here. And so here we have B, and here we have A. So this is the configuration. So my Z is reading A. If my Z is reading A and it changes to Z prime, overwrite C and stays neutral, it's this is the next configuration, the part of the next configuration. And it has a code. So my function is supposed to take in this natural number and spit out this natural number if this happens. And you know, there's only 3 stories: going right, going left, overwriting C. So it's supposed to return this and supposed to return this. If this is the case, this is the case, and this is the case. And I say that it returns 0 so it's supposed to act on every natural number, right? It's what I'm constructing it so that it's defined everywhere. And if you give me a natural number which is not a code of anything, it's not a code of 3 symbols like this, which I can check because I can just go back in every symbol and check, then if it's not a code, I return 0. But if it's a code of some string, then I return this if this is the case, this if this is the case, and this if this is the case. Now I claim that this function is μ-recursive. Why? Because this function only takes finitely many values. It's a function from states and alphabet that maps to states, alphabet, left, neutral, right. These are all finite things, and this is computable. We showed this that this is, if your function has a finite image, it's computable. You just check on every single possibility and you compute it there. So this function is computable. Checking whether this computable function equals this is computable again. So this thing is computable. So it's a case split between computable things. So this thing, the delta prime, the delta tilde is a computable function. So this next step function, which now basically what it does, it just translates the next configuration thing into operating on numbers, is a computable μ-recursive function. And after this, it's only a bookkeeping. And I'll show you why. So let's make it smaller. By the way, these are the only cases I need to consider, because I will never go to a blank, because this is how I will proceed. Let me show you how I will do this. How does my Turing machine start? My Turing machine starts with the initial in state Z0 and reading word W, and I will just put 2 blank symbols on the right and 2 blank symbols on the left. This will be my initial configuration. Blank blank, start state, whatever is my input, blank blank. This is my start state. Now this corresponds to a number. I know this. I can construct a number such that this corresponds to. Now I have this number. I'm looking at this number. From this number, I can extract exactly the code of the state. I can exactly extract the code of what letter my state is looking at and the previous letter. So I know the code of the state. I know code of the letter that the machine is looking at, and the previous letter. Then I apply delta to this. So I compute the next number such that Z will operate on B, whatever this thing does. Then I will concatenate it with the code of the tail and of the, well, not the head, but the suffix and the prefix. And I will again concatenate it with the code of blank symbols. So at every single step, I'm basically adding blank symbols. So I start here, I do something. So my Turing machine makes one step, something happens on natural numbers, I add one more blank symbol. Again, on the next step, I again add the blank symbol. On the next step, I again add the blank symbol. So I'm increasing my thing. This guarantees that my Z0 will never cross the border, because at most it can make one step at a time, and every time the B is added on both sides. But now my delta X is a code. I'm no longer looking at the computation, rather I'm looking at natural numbers. So let me explain in Georgian what is happening. So okay, so this delta X, so what does this delta X represent? Just let's think about it. So X is a code of my number, so it's a code of some configuration. Delta x represents the code of the next configuration, added with 2 blanks. This is all there is. And now, what if I make 2 steps, 3 steps, 4 steps? What if I make n steps? It's very easy. If you primitive recursively define, INX is what? INX is a function that takes input x is a natural number, and gives you a natural number after n steps of the Turing machine. This delta x was just 1 step, right? So it takes in natural number and gives you a next natural number according to the Turing machine step. And INX is supposed to give the nth step. How do you define it? Recursively, very easily. I0x is just x. So let's look at our example here. I wrote this 3, so let's erase. So it's too overcrowded now. So this is my step. Let's erase this again. So let's say, maybe I wrote this a better version of this, right? So yeah, here I wrote that, let's say, so this was my configuration and this was my next configuration. And then let's say my next configuration corresponds to this number. I don't know what this is. So let's say this corresponds to this configuration, and the next configuration corresponds to this number here. Okay. So this is just then I would say that delta 2, 1, 3, 4, 1, 2, 3 is equal to 3, 2, 1, 3, 4, 1, 7. Okay. So delta is just operates on natural numbers, and it just gives you the next natural number according to and we just proved that this thing is mu-recursive. And what I want to do is I want to apply delta again and see what happens. So INX is basically applying delta n many times, and this is exactly what it says here. I0x it just returns you x, and IN plus 1x is delta applied to INX. So you're just making n steps. Okay, there's nothing critical here. And now we come to the crucial point. The crucial point is, okay, let me ask you this question and maybe you can respond. Let me pause this and then you can. So see, exactly as you said, here is what you said. So it's written here. So Tx is the smallest j, Tx is supposed to measure how many steps does it take until the machine is finished calculating. Tx is the smallest j such that when I make j many steps starting from x, so x is my initial number, natural number that I'm looking at, I'm made j many steps, and this z denotes I check, so I look at my number and I check the code of the state. This is what this z does. And if the code of my state is the code of the end state, then it's finished. So j is the smallest j such that when I make j steps starting from x, the state of that number is an accepting state. Okay? This might never happen. So this is an unbounded minimization. It's looking at the smallest j that this happens, but it's not a for loop that goes. You have to continue doing this infinitely, because if your machine never finishes, you will never find this. So this might be undefined. This is a while loop. While zijx is not in psi I, increase j by 1. This is what it is. This is a while loop, an unbounded while loop, and it's an unbounded mu operator, and this may not be defined. And this is the crucial point where you're using that you are not in primitive recursive functions. Everything before this was primitive recursive. Remainder, rounding down, adding and stuff. But this here, if you want to calculate how many steps your machine is taking, you need an unbounded mu operator. So I can calculate Tx, but this calculation might not be defined, and this is because this, but in mu-recursive functions I can still do this because I have an unbounded mu operator. And then, if I know what Tx is, what is my resulting end so what is my final number? So the final number is very easy. If I know when to finish, I know that I have to take, so tx counts how many steps do I need to take until I finish. So I take that many steps from x, and this is my end configuration. And only thing left now is to translate Rx back to the output. So Rx is just a number, and I want to translate now this to a string. But I also didn't tell you, I skipped over this part, how to code this. So I said that I will code, so this was my initial thing, and I will code this into numbers, then I will do my magic, next number with delta. Then I know that I'll have to take tx many steps. I will take tx many steps, and that will be my end configuration. Even though tx might not be defined, and I will have to take infinitely many steps. And so only thing I have to do is now tell you how to translate from the final number into an output, and also I have to tell you a preprocessor how to translate this guy here into a number. This is actually very easy. So one might even leave this as an exercise, but let's do this. So at least it will be on the recording and you will see. So okay, let's go back to page 1. I mean, initially I had a function that takes r many variables and returns n0, and it's computed by a Turing machine. What did I mean that it's computed by a Turing machine? This means that if I start my Turing machine with binary representation of x1, x2, x3 up to xr, so it takes r many variables, each one I represent binary. I start my z0 on here, and I put 2 blanks on the right and 2 blanks on the left. Then after I start my machine here, it should output something in binary. So first I want to code this. My preprocessor takes r many variables, and it gives you, so what does this thing do? Let me show you on the nose. So let's say I have a function, just for simplicity, xy. So this is a function from n to n. So it has, so let's write it this way. So n squared to n, like this, right? So it takes two variables, and it just, let's say fxy, just for simplicity, is x plus y. And this thing is computed by a Turing machine. What this means is when I start on a binary representation of x1, I put a hashtag and I do binary representation of x2, and then I do blank and blank, blank and blank here, and I start my Turing machine, it should end with binary representation of x1 plus x2. This is what it means. And what my preprocessor is doing, my preprocessor on, let's say, x1 and x2, it produces the code of this thing here. BB binary x1 hashtag binary x2 BB. So in particular, let's take P35 is supposed to be a code of blank blank. What is 3 in binary? Samyani binary shogurari. 1 hashtag. What is 5 in binary? 101 blank blank. This has a natural number corresponding to it, right? Let's use our code. So in code, I think B was 3. So this is 3, 3. 1 was 2, 2 hashtag. I don't remember what hashtag was. Let's say, was it 4? Then 1 is again, 1 is 2. 0 was 1, 2, and blank was 4, 4. So this, huh? However, so I don't know what P is, by the way. That's the correct. What is P? What is P plus 1? But let's assume this guy has, let's assume, just for simplicity, the alphabet is this thing only. This is the only thing we need to calculate this kind of things. And let's say, I don't know how many states does it need to add things. However many, let's say Z's, for our simplicity, 5 states. I can always do this, by the way. If I cannot always do this. If I'm using less states, I can do this by just adding dummy states. But if I'm using more states, I cannot do this. But if this is the case, I don't know which program you wrote to compute the addition, but however many things, if this is the case, then this is the code. But what my I just want to show you what my preprocessor is doing. The preprocessor is taking the input and giving you the code of the start configuration. And I just want to explain what this thing, so this is exactly what is written here in general, but then it's explained how you do this. How do you produce this code? Remember somebody was calling me. Okay. So remember in exercises, you had this exercise there that if you have a function, a g and h, then if h and x is the sum of g up to n like this was called bounded sum, and you also had bounded product, then this is primitive recursive, and this is the solution. It's very easy. You can write it as primitive recursion, but let's say that you solve this exercise. So if you have two functions and one is just the sum is defined this way, as you can see here. Where's my laser? So as you can see here, if it's defined this way, then if G is primitive recursive, then so is H. But I will use this like as here, but I mean, this is an artificial problem that we are creating here, so might as well. Yeah, let's just look at it. Okay. The artificial problem is that here I have in decimals, and here I had it in binary. So first, how do I convert from? First, I have to convert 3 to 1, 1, and I convert 5 to 1, 0, 1. I have to also do this in order to write the code of this one, right? I asked you, and you told me, but if you're coding it, you should be able to convert 3 to binary and 5 to binary. And this is the first step here, how to convert to binary. So let's say x is something, so x is a natural number, let's say 3 or 5. And how do I find the code of the binary representation of x? First of all, what is the length of the binary representation? It's the smallest j. I'm not going to emphasize it. This is the same thing. So can you, by the way, tell me this? Exactly. So if you want to find the length of x, then it's the smallest j. It is a bounded operator up to x plus 1. That 2 to the power j is bigger than x. And now, how do you find the bits of the binary representation of x? Let's say the binary representation of x is just some string from 0 to length minus 1, right? So you know the sx now, so it's a string from 0 to sx minus 1, and yi is basically the select from xi. It's the bit, the ith bit of the binary representation. It's again the same thing. You divide x by 2 to the power I plus 1 divided by 2 to the power I and round it down. This gives you the ith bit of the binary representation. And then what is the code of the binary representation? It's the same thing. You look at the code of your bit. This bit is 0 or 1, and you write it in the powers of p plus 1 to the I. So you change your 0, 1, 0, exactly what I did here in the representation. When I looked at 1, 1, and I changed it to 2, 2, because I know that the code of 1 is 2, and I wrote it as in the base of p plus 1 to the power I. In my case, p plus 1 was 10, so it was easy. So you do this, and for your preprocessor it does this for every single input, and it also knows the codes of hashtags, and it also knows the codes of BB, and it just concatenates them all together to arrive at what I wrote here. Because I knew the codes of Bs, I knew the codes of hashtags, and I just concatenate them together. This is what the preprocessor does. Nothing fancy, but you have to. This is, by the way, we chose so that our Turing machines work on binaries, but I might have chosen that they worked in decimals, and then I wouldn't have to do this at all. Because so what I want to emphasize that this is artificial. And now the final step is the post-processor, meaning that now let's say my Turing machine has finished working. Let's open it up all the way. So let's say my Turing machine finished working. So it finished in bunch of blanks because as many steps as it took, I was adding blanks. So I have bunch of blanks, an accepting state, and the output. What I'm supposed to do is I want to extract the output and revert the code. So again, first I cut off the leading bees. I'm going to go fast here and I leave it as an exercise. So first of all, I'm looking at the code. So I'm looking at the natural number. First I have to guess, okay, these are all blanks in the beginning. Basically, I find where the state sits in my code, and starting from the state, so the state sits somewhere, and I want to get rid of all the bees and the state, so I just take the suffix of my number at the place where state sits +1. Then how do I find the first position of the blank? This is f2x, is the smallest I, such that when I look at each and every code, it's the code of blank, exactly. And then cutting off, so f1 will cut off the beginning of bees, f3 will cut off the ending bees, so it will take, so you're taking the prefix, so of f1x will cut off the beginning, the starting bees, then f1x, then in the remaining thing it will, so you cut off the beginning bees. What f2 will do, f2 will cut off find the position of first bee, and you take the prefix of that one side to the left, and it will exactly cut out the binary representation of y it should be. So you will not have y, you will have binary representation of y. So you will cut off here, and you will have the code of binary representation of y. And let's call this guy z for simplicity. And now the only thing left is to translate binary, so the code of the binary representation into the actual number. And how I do this, I still have 9 minutes. So let me pause this and explain. Next slide. So how I do this is that I initially, remember, here, where was this? When I chose my coding. I actually did this way. I will always do it this way. I will always put 0 to be mapped to 1 and 1 to be mapped to 2. I will just take a convention that when I'm looking at the 1s and 2s, I know that they are codes of 0s and 1s. So exactly now that I will extract, so now I'm looking at this number, what I can do is, I know that, okay, this one, so what I did is these ones are blank. This cannot happen, by the way, because the beginning and end should be the same. It will be something like this. Aka. So it should be something like this. So what I will do, I will cut off something like this, I will cut off something like this, and then this is my output, whatever. And I know that 2s are basically 1s, and 4, well, this is what I wrote down here, this is the start configuration. Then I will apply something, apply, and in the end I have the output that looks like blank, blank, accepting state, and just binary representation of single thing, blank, blank, and bunch of blanks. This corresponds to a number. This will be something like 3, 3, 3, 3, bunch of 3s. Then there will be whatever the state is, let's say 7. And then there will be something. 1, 2, 2, 1, 2, 1, 1. And then there will be a bunch of B's. And what my F's are doing are cutting this thing off, cutting off 7. And now this will be translated into a binary. I know that 1 is 0, 2 is 1. So it will be something like this. This cannot happen, by the way. It will start with 2. So this will be something like this. And now I have to translate, so 2's are 1's and 1's are 0's, and now I translate this into decimals. This is what this thing is doing. So it says that 0's are mapped to 1, 1's are mapped to 2's, and what I do is how do you go from binary into decimals? You just do this exactly. You extract the ith. So what this portion here does, it extracts the ith bit, and I subtract 1 because if this string is 1, I should get 0. If this string is 2, I should get 1. So this is why I subtract 1. So this is 1 or 2 always, so I get 0 and 1, and I multiply by 2 to the power I, and in the end I get the decimal expression of y. This is an exercise basically. So let me pause this and I will explain. Yeah, I should have probably recorded this, but anyways, so this is basically an exercise easy. So you can see that I wrote this down, so this also translate this back to y, and this basically finishes the proof. I will just show you what it does. So how do you compute your function? First you start your input, you change, so what does P do? P is a preprocessor, it changes to a natural number. Then what R does is R is the most important part, so it does all the steps according to your Turing machine, and Q then translates your final natural number back into an output. So your function is now computed by mu-recursive functions. P was mu-recursive because we only used mu-recursive things. R was mu-recursive, Q was mu-recursive. Their composition is mu-recursive, so if your F is computed by a Turing machine, you can do this, and it's computed by mu-recursive things. And by the way, let me just mention one more thing. So we proved the Kleene normal form without even mentioning this. This is a very famous, so Kleene is this guy, and he has a normal form that says this, that if you have a mu-recursive function, then there are two primitive recursive functions such that your mu-recursive function, so basically, let me explain it in different words. So how do you construct a mu-recursive function, right? You start with constants, projections, concatenation, their composition, and so on and so forth, and then you do recursion, you maybe do unbounded minimization, then do something again, then do unbounded minimization again. So in general, you don't know how many times are you using composition, how many times are you using projection, how many times are you using unbounded minimization in general, right? But we just proved that you really only have to use unbounded minimization once when you're computing Tx in R. So for any mu-recursive functions, we showed previously in previous weeks that if you have a mu-recursive function, there exists a Turing machine that computes it. If there exists a Turing machine that computes it, there exists a one-tape Turing machine that computes it. If there exists a one-tape Turing machine that computes it, then you can create this P, R, and Q such that you use bounded minimization only once. And here is the Kleene normal form that just says that any mu-recursive function can be constructed from projection, constants, and successor, minimization, primitive recursion, so that you only use bounded minimization once. This is the Kleene normal form theorem, basically. And we proved this because you can do as I explained just in a minute. So let me stop this so we also have time for